Let's welcome Kobe.
Thanks a lot. Hey, good morning, guys. Can you all hear me all right? Cool. Thanks for coming out. So today we're going to talk about spread spectrum signals and hacking the Globalstar Simplex data service. Yes, that's satellites. So first, I wanted to give a kind of a shout out to whoever rebooted the elevator computers this morning. That kind of got the day started off right. Anyway, but first, who am I? I'm actually a mechanical engineer that loves computer security, and I currently work at Synac on the R&D team. I first got interested in satellites and radios when I got my ham radio license a while back. Guess, ladies, that's my call sign up there, so be sure to radio me. I'm single. But anyway, what is this company, Synac, that I work for? Basically, we're a startup with a new spin on security for the enterprise. We have an army of vetted security researchers that hack our clients on a bounty basis for some pretty crazy payouts. If you have spare cycles and want to hack for money, come join our red team. And if you're worried about security, come talk to us. We have a sweet booth out in the lobby. I think we got some free drinks and coffee and stuff out there, so come say hey. I'll be around if you guys want to chat more about this research. All right, so a brief introduction. A little bit of motivation. Why am I doing this? I wanted to try something new. I was kind of frustrated with the talk diversity lately. Same software stuff, same exploits. Satellites, I think a lot of you would agree, tend to be kind of like the ultimate hack. And there seems to be one every year, but a lot of them are like very theoretical, and you can't really go home and apply the knowledge you learned. And I've been doing a lot of research at Synac on location-based privacy, so looking at location monitoring satellites seemed kind of like a good fit. But bottom line, I wanted to take a stab at something different and hopefully inspire some collaboration and further research in a kind of an unexplored area. I'll be releasing some tools later today, maybe tomorrow. I haven't had time to get them up yet, but they'll be on GitHub. I'll have the links at the end. So hopefully some of you guys that are interested can go try this at home. So what are we going to learn? First, we're going to talk about the basics of RF signals and modulation, an introduction to what spread spectrum is. Then we're going to select a target and reverse engineer it, and then hopefully exploit that target. And I started doing this research kind of on my own in my spare time, just for the heck of it. So I wanted to keep it on the cheap. So we're going to do this all for less than $1,000 to keep it pretty accessible to everyone here. There's quite a bit of material to cover, so I'm going to move pretty fast and hopefully leave enough time for questions at the end. But all the resources will be online. So my intent is to keep it all fairly high level to give the generic hacker the skills they need to analyze satellite systems. Really, hopefully, all you're going to need coming out of here is a high school mathematical knowledge. So let's talk about targeting. How do we pick the system that we're going to hack? There's lots and lots and lots of potential targets out there, these just being a couple. And they operate on a variety of frequency ranges. But picking the right one was key. So the technology needed to be, namely, consumer accessible and cheap, because this was a side project and I was funding it by myself. So I wanted to keep the barrier to entry pretty low. I wanted them to be popular, and so we found a bug would be pretty high impact across the board, and we'd have some juicy stuff to talk about. I personally was familiar with Globalstar's Spot line of consumer products. And personally, I think they're fantastic. I use them out while backpacking. And they also make asset trackers for your car or yacht in case it gets stolen or something like that. And they make personal locator beacons when you're out backpacking. If you need help, you break your leg, you press a button, and it tells search and rescue to come get you almost no matter anywhere you are in the world. So I started looking deeper into this technology. And it turns out that their commercial offerings and even some like military offerings, they use the same technology as the consumer tech. So this seemed perfect. The implications were very broad spread. So basically I could buy a dirt cheap device to research, and the research would translate to all these expensive devices. Not to mention anything found would be pretty high impact because these things are deployed everywhere. So I looked at, my research focused on three main devices, the Globalstar Spot Trace locator beacon, the Smart 1A, a commercial asset tracker mostly used like on shipping containers, and then the Spot Gen 3, the personal locator beacon. But anyway, so where is the satellite technology used? Really, it's used everywhere. The tech is designed to be integrated anywhere low bandwidth off-grid communications are needed. Most interestingly, it's used in SCADA systems, big gas and oil operations, military, and predominantly asset tracking, so think shipping containers and other expensive things, armored cars, interesting stuff. So all this tech operates on what's called the Globalstar Simplex data network. But how does the data network work? In the case of asset trackers, devices can also send back arbitrary data as well. The tracker gets its location from GPS satellites, and then it beams its location and other metadata up to Globalstar's satellite. That satellite simply forwards that information back down to the ground stations all around the globe, and then it decodes and processes the data from the packet, forwards it on through the internet to Globalstar's backend infrastructure or to a user's custom infrastructure. I kind of liken this technology to SMS for the satellite world. Very short. The data packet size is about 72 bits. So the Globalstar system is a series of low Earth orbit bent pipe satellites. And the way a bent pipe system works is that essentially what goes up is exactly what comes down. It just kind of shifts the frequency and repeats the data. And this keeps the cost of the satellite low, as it's pretty dumb and doesn't do any processing. And it keeps future usability really flexible. But notice that the data link is in one direction, Simplex, the Simplex data network. So how the heck is that reliable? Well, it turns out that each data packet is sent multiple times to ensure successful transmission. So, two, three times. And truthfully, I've found from testing, these things are crazy reliable. I can leave a transmitter in my trunk, like shielded, and it still gets out somehow. It's pretty wacky. So what's the deal with these ground stations that we're talking about? It turns out there's hundreds of them around the globe, and they handle all the reception of the satellite data. And then there's also two main, operations control centers that handle the actual operation of the satellites, that control, orbits, positioning, et cetera. One of those is located in San Jose, California. I forget where the other is, but you can see a picture of that there on the right. The ground stations look like these big antennas on the left. So here's the coverage map from Globalstar's website. You can see there's patches where there's no coverage, namely in the middle of the oceans, and that's because there's no ground station there to receive the satellite data. Each ground station provides a few thousand-mile reception window. So you can see down in South Africa there's a big, clear blip. They actually just added that one recently to add coverage down there. So I always like to do a little bit of groundwork first, just to get an idea of a client's general security posture. So I had to look at their website, and I was having trouble signing up for an account. And I tried to log in, and wait, what's this like? Looks like a SQL injection to me. So I'm starting to get like that warm hacker fuzzy feeling, and I know this is going to be like a fun target to hack on. And I'm digging a little deeper. And it turns out that the data from the ground stations appear to be forwarded to clients over FTP and HTTP. Yeah, there's no S. So it might be just easier to sniff this data over the internet instead of over the air, but that would be too easy. So I'm thinking things are looking pretty good in general, and yeah, let's move forward and try to break this. So let's dig deeper into the actual satellite system. So we need to gather our intelligence. How do we go do that? Where do you look for hardware information? Of course, Google. Everyone Googles everything. But the FCC database turned out to be really the wealth of information. Essentially, if you have a RF device in the US, you have to register with the FCC to make sure you're not transmitting other people's frequencies, and it conforms to all the laws. And so you end up submitting your papers, your design docs, and it's, oddly enough, they share this all. Also, academic papers, there's been a lot of studies on the Globalstar system, as well as I found a lot of leaked integrator spec sheets, which was fantastic. I also wanted to make sure that someone else hadn't already broke the system. So I looked for any prior research. It turns out Travis Goodspeed, I'm sure many of you guys know him, he looked at the Bluetooth protocol of one of Globalstar's devices. Just kind of the protocol, it talked to a phone, and so you could send messages through the Globalstar device over the network. And then a guy by the name of Natrium42 looked at the GPS microcontroller interface on board one of the old spot personal locator beacons. But I wanted to dive a little bit deeper. This was all fantastic research, but it didn't really deal with the satellite communications themselves. So looking a little deeper in the FCC database, I found that a chip called the STX3 kept coming up. Turns out it's one of the transmitters used by the Simplex data network, designed for integrators to put these creations in their devices. It's low cost, low power, and tiny. You can see it's about the size of the quarter, and that thing will talk to a satellite. And there's some nice diagrams that came along with this thing that reference kind of its inner workings. In all these diagrams, I kept seeing this DSSS and BPSK coming up. But we'll talk about that more in a minute. I didn't really know what they were, but I figured they were probably important. So the FCC databases also came up with the various frequency ranges that Globalstar uses for the Simplex data network. And in the case of these specific devices, it also mentioned their frequencies. They operate on about 1.6 gigahertz. So I kept digging around some more, and I found this leaked manufacturer spec sheet from a company called Axon. And it's a company that used to make these transmitter chips licensed by Globalstar for the Simplex data network. And it referenced all these wacky parameters that really didn't make any sense, but I couldn't help feel like they were important. So of note, the summary of this doc says that we see that DSSS again, and something called a 255 chip PN sequence at a rate of 1.25 megachips per second and a reference data rate of 100.04 bits per second. It turns out these are all parameters for spread spectrum modulation and for this specific system. But we'll talk about that more in a minute as well. So before we talk about the spread spectrum stuff, let's have a brief review of waves and modulation. So remember that radio waves, or radio signals, are transmitted on radio waves. And data is encoded on waves by modulating various parameters of that wave. And remember that waves have three main characteristics that we can modify. One being wavelength, essentially the frequency, how many cycles of the wave per second. And then the phase, the position of the wave relative to a fixed point. And the amplitude of the wave, essentially how high it is. And then, when we look at waves, we have a couple of different ways to look at them. You're probably most familiar with the time domain representation, where time is on the x-axis and amplitude is on the y-axis. But often working with signals, we look at what's called the frequency domain representation, where frequency is on the x-axis and amplitude is still on the y-axis. So this frequency domain representation essentially shows us what frequency components make up a signal. If you looked at a frequency domain representation of a pure 100 kilohertz sine wave, it would show up as just a sharp spike at the 100 kilohertz mark on the frequency domain graph. And sometimes we call this an FFT plot. But oftentimes signals contain many different frequency components, and so the graph will take on kind of a really unique shape. So different types of signals have kind of a visual representation. So now that we kind of know how to look at them, let's start and see how analog modulation is done. We're going to look at both AM and FM, both of which you guys probably listen to in the car, AM/FM radio. So to send an AM signal, essentially you have a carrier wave at the desired frequency you want to transmit on. And then you vary the amplitude of this wave according to your data, which we call the modulating signal. The resulting signal is what gets sent over the air, and you can see the resulting signal down there on the bottom. Notice how we varied one parameter, amplitude, to send the data over the air. Instead of modulating the carrier analogically, we could have also simply varied it between two discrete amplitudes to encode digital data on this wave as well. The method of encoding digital data over AM is often called OOK or ASK for on-off keying or amplitude shift keying. And we can do the same thing to frequency modulate data, except we vary the carrier's frequency according to the modulating signal instead of the amplitude. Again, we could have shifted it between two or more distinct frequencies to digitally encode these data symbols. And this method for sending digital data over FM is called FSK, frequency shift keying. And so, as we talked about, digital AM is called ASK or OOK, and digital FM is called FSK. But what if we wanted to vary the third parameter, the phase, in a manner that's, we can do this in a manner that's called phase shift keying. And we can do that to encode data on a wave using just the phase. So for this talk, we're going to focus on specifically BPSK. Remember, we saw that earlier in the spec doc. It stands for binary phase shift keying. Essentially, it's alternating a wave in and out of phase 180 degrees in order to encode binary data. And this 180-degree phase shift is simply achieved by flipping the wave upside down or just multiplying it by -1. So here, each cycle of the wave corresponds to one symbol, a bit in this case. Okay, so we have the necessary knowledge on how signals are modulated, so let's go one step deeper and talk about how we turn these into spread spectrum signals. Basically, spread spectrum is a way to take a narrow band signal, one that doesn't take up too much bandwidth, and spreads it out over a much wider frequency range. And this gives it the ability to be, really jam resistant. It introduces a property called processing gain. Essentially, the more you spread a signal, the more gain you get at the receiving end. Essentially, you can transmit further. This processing gain actually allows for a spread spectrum signal to be received even if it's below the noise floor. So spreading the signal also allows for what's called CDMA properties. This stands for code division multiple access. You may have heard about this, with your cell phones and such. What that means is that multiple devices can transmit on the same frequency at the same time. Think cell phones. This is achieved through each device having a unique spreading code. Remember earlier we saw that reference to a PN code? That's kind of the same thing. So there's two main types of spread spectrum, DSSS and FHSS. DSSS stands for direct sequence spread spectrum, and FHSS stands for frequency hopping spread spectrum. And the difference is that DSSS operates around one single frequency, whereas FHSS hops between multiple frequencies. So on the left you can see the DSSS form at one peak, and on the right the FHSS at 4 peaks. It's hopping between 4 frequencies. So for the sake of this talk, we're going to talk only about DSSS. And remember, we saw that reference in that spec sheet earlier. So to create a DSS signal, in this case, a relatively slow BPSK signal, remember 100.4 data bits per second from the spec sheet, we mix it with a very, very, very fast pseudo-random signal, that PN sequence. And the resulting signal contains all the original information that is spread out over a much, much, much larger bandwidth. And so here you can see the data BPSK signal on the left, and then on the right we spread it out to 1.25 megahertz. That's 12,500 times wider. And notice the shape of the waveforms are very similar, in fact, and that'll be important later. So here's an example. Our data signal is really just 0 and 1, shown there in the blue, modulated very slowly. Our pseudo-random sequence is a binary sequence that changes much, much, much faster, essentially a high-frequency signal, shown there in the green. If we mix those two together, we get a resulting signal with high-frequency components. They're the resultant there in the red. Now, if we wanted to recover the data from that resultant signal, we simply mix the output signal with the pseudo-random signal one more time, and the original data falls out. So you can see we mix that resultant in blue with the pseudo-random in green, and the data signal comes back out there in the red. So this is kind of how you spread and despread a spread spectrum signal. Now a little bit more about these PN sequences. What they are, they're periodic binary codes that have strong autocorrelation properties, meaning that they are a binary sequence that repeats over and over and over and over again. And just as an interesting piece of information for those that you might want to dive into the nitty-gritty, they're generated commonly using linear feedback shift registers. So for this research, we're looking at a specific type of PN sequence called an M sequence. And again, we saw that in the original spec doc. And what's interesting about them is that about M sequences is that they correlate strongly with themselves at a phase shift of 0, but very poorly with themselves at any other phase shift. So let's take a look. Here we're comparing a very short M sequence to itself, the M sequence being 0, 0, 0, 1. It has a perfect correlation of 4, shown there on the left. But if we shift down there on the bottom, we shift the M sequence 1 to the left, we can see that the correlation goes to 0. And then we shift it again, it's still at 0, and one more time it's at 0. If we finally shifted it one more time around, we'd be back at the original phase shift, and it would have a very strong correlation of 4. And this is nice because it makes searching for a PN sequence in a signal really, really easy. So let's talk about decoding theory. This is all simple in theory, but it's actually more difficult in practice. So in theory, you simply mix the signal being received with the appropriate PN sequence, and the data signal will emerge. But in a perfect world, our transmitter and receiver are going to be tuned to different frequencies. So they'll never be on the exact same frequency. So we need to accommodate for this frequency differential at some point. Also remember that if the PN is not properly aligned with the data, this won't work. We'll get a garbage signal out. So we need a way to phase align the PN sequences. So keep thinking on how we might do that. And I'll give you a hint. We use the autocorrelation properties of the PN sequence, but we'll talk about that more in a bit as well. So we have the theory down, but we need to put it into practice. So time to build some hardware so we can do this. So to do this, I use a software-defined radio along with Python and GNU radio to write my code. I use the USRP B200. It's about $600. It's a fantastic board. It's from Edis Research. I strongly suggest it. I also needed an appropriate antenna that I ended up actually just getting off eBay. It's a Globalstar antenna, oddly enough. And for those who wish to try this at home, note that these Globalstar antennas are left-hand circular polarized. So you can't just use any specific antenna at 1.6 gigahertz. It has to have the right polarization. But that's a little bit out of the scope of this talk. And for those of you familiar with RTL, SDR, the really cheap TV dongle software-defined radio, unfortunately it won't work for this. It doesn't cover enough bandwidth. It covers maybe about 2 megahertz, and we need just a little bit more than that. So unfortunately, you'll probably need a more robust SDR. We also needed a low noise amplifier for receiving weak signals. I really wanted to try to receive some actual data. And the supporting cabling and voltage regulators to supply it. So I got this specific LNA from a company called Mini Circuits. I really like these Dimension Engineering any volt regulators. So basically, it's a DC step up or step down regulator for pretty much any voltage. Strongly suggest this stuff. Now, anyway, at this point, I packaged it all up in a nice box because these things are pretty fragile, and we all know that hackers are clumsy, or at least I'm really clumsy. I didn't want to break it and piss someone off. So I mounted the antenna on the outside of the box so we can aim it kind of wherever we need to, but it'll still be kind of all together. I brought it with me. You guys are welcome to come up after the talk and take a look, play with it, poke it, whatever. So just know that this is what we're going to use to do our research. But, so how does this hardware work? It's kind of, a mystery black box. It listens for radio waves, which are, technically analog. They're out there in the real world. And it converts them to digital data so a computer can process them. And it does this by taking samples of the wave at discrete points in time. Now, this guy named Nyquist back in the day came up with the realization that while sampling, you need to sample at least twice as fast as the signal's fastest frequency in order to reproduce the signal accurately. So a real world example that might help you get your head around this is that the human ear can't hear frequencies higher than 20 kilohertz. Now, if you remember, CD audio is sampled at 44.1 kilohertz. That's just over twice the human hearing range. So that's this in practice. So you should also know that these software-defined radios, they use what's called IQ sampling and modulation to receive and send signals. Now, this topic is a little too much to get into now. This could be a whole conference talk of its own. But know that for each data sample taken, 2 values are recorded: an I value, the in-phase value, and the Q value, the quadrature value. And using IQ modulation has strong benefits for doing signal processing in software. So if you're interested, I suggest you check out this YouTube video for a good explanation. It's really fantastic. But bottom line, you don't need to understand it for the rest of this talk unless you're going to try the satellite stuff at home. Happy to talk with you guys more about this later. So the first step to decoding a satellite transmission is we need to figure out this PN sequence. That's really the key to intercepting this data. So let's put our hardware to work. So remember that we're looking for a signal, the PN sequence, that's 255 bits in length. It repeats over and over and over and over again. And it repeats at a rate of 1.25 million chips per second. Now, I should mention here that a chip is the same thing as a bit, but we name it differently so that we can distinguish it from the actual data bits of the original data message that we're mixing it with. Now, interestingly enough, we can treat DSSS BPSK, a spread BPSK signal, the same we treat regular BPSK. So check out this graph on the left. We can see that the BPSK signal on the top shifts the wave at its transition, but once every several wave cycles. The DSSS BPSK signal shifts the wave much, much, much faster. In reality, it's even faster than this, but in the same way as the BPSK signal. So it essentially means they're the same thing. So this means we can use an ordinary BPSK demodulator to receive spread data. Now, the downside of receiving data this way is that we don't receive any of the processing gain that we talked about earlier. So this technique really only works well over short distances, but it's perfectly legitimate. I was seeing it maybe over like 100 feet or so in the lab, and that was with my code. So to accurately receive this data, we need to set our hardware to sample correctly. And we have to meet a few different criteria, three specific criteria. First, the USRP, the software-defined radio, can only sample at multitudes of 32 megahertz. We also need to sample twice as fast as the highest frequency component of the PN sequence, which is 1.25 megahertz. And this is due to the Nyquist sampling theorem we talked about. We also need to sample at a rate that provides an even number of samples per symbol. In this case, an even number of samples per chip. So we achieve all this by sampling at a rate of 4 megahertz, and then resampling the signal, essentially just interpolating extra data points into it to get a resulting upsampled signal of 5 megahertz. And what's special about this 5 megahertz signal is that it has a sampling rate that corresponds to 4 samples per symbol. But now, how do we use this to get the actual PN sequence? Well, we know from doing some calculations that the PN sequence repeats 49 times for each bit of data. And since the PN sequence doesn't cross any bit boundaries, it repeats 49 times within a bit, if we XOR the PN with a fixed bit of data, that initial bit, the resultant should be the PN code itself. So let's use GNU Radio to decode the data signal as just regular BPSK in the appropriate settings and output the data to disk. So here you can see a chopped GNU Radio flow graph that I used to do this. You see the PSK demodulator there on the right, the big block. It includes the setting of 4 samples per symbol that we talked about. The PSK demodulator then outputs the decoded symbols to a binary file that we can examine later with a hex editor. So looking at the data in that hex editor, we clearly see that there's a repeating sequence of data, 255 bits long. And sure enough, that's the PN code. And it turns out that's actually the keys to the kingdom. This code is used by all Simplex data service network devices to encode their data. So now that we have the code, and by the way, that code will be online later if you guys want to use it, let's despread some of the data. Now you may recall that we need to mix the PN code with the incoming data signal to retrieve the information. And if all goes well, we should expect our output signal to contain a very strong narrow band signal shown as a sharp spike. That's going to be our original data signal kind of popping out. So above is what a normal Simplex data network signal looks like, the DSSS packet. And the graphic below depicts an illustration of similar to what we should see, that one sharp spike emerging and the rest kind of being suppressed. So now before we begin, it's important to know that working with these signals is actually super computationally intensive. Receiving a signal at 4 megahertz with a software-defined radio works out to an incoming data rate of 30.5 megabytes per second. So for the purposes of this work, we're doing all the data recording now, and then we're going to post-process the data that we record. Eventually, it'll be possible to use more robust custom hardware, think FPGAs or CUDA, to do this work in real time. But that really sounds kind of like a pain in the butt right now until we prove this out. So a big thanks to my interns. I think a couple of them are sitting right up here, for optimizing the hell out of my code. Previously, it took about a minute to process a data packet. I think they have it down to about 40 seconds right now. Hopefully, we can get it down a little bit more. So how do we despread the data? First, we need to lock onto the mixed PN sequence in the signal. We do this by correlating the received data signal against the recovered PN at each point in time. Essentially, we're sliding that recovered PN sequence against the received signal and correlating every step of the way. If we plot the correlations over time, when the PN is perfectly aligned, we should see a sharp spike in correlation, and that's what those spikes there you see are. This is how we know when to mix the two signals together to despread the data. So if we align the PN on the first correlation spike only, due to some frequency mismatch, we'll fall out of correlation over time, shown there on the graph on the left. And we fix this by adjusting the PN forward or backward at each and every correlation peak to ensure its alignment. So at this point, once we're in alignment, we mix the PN and the data again together, and then we should dispread the signal that way. So let's try that and see what happens and look at the correlation. So shown here on the left, we actually get a really consistent correlation. And you can see it oscillates, a little bit over time, but overall, correlation is relatively consistent. If we zoom out and look at the correlations over time of the whole packet, you can see positive and negative correlations, and these correspond to actual bits of data. So if we look, this was the code that despread the data. If we look at that on the frequency domain representation, the signal coming out of the software to spreader, sure enough, you see that sharp spike in the center, indicative of our original data in question. And this means we successfully despread our data. If you zoom way in on that peak, 12,500 times in, we can see that the waveform actually looks like a BPSK signal, and is operating, if you can't really see the numbers down below, but at about 100 hertz, which we know is the data rate in question of this network. So things are looking really promising at this point. So now that we're seeing data packets, we actually need to decode them. So if we look at the time domain representation of that signal, you can actually see the data bits coming out over there, up there on the top. And so, to process this, we clean up the signal a little bit. Namely, we low pass filter it and then pipe it just to a regular BPSK demodulator. So at that point, data just starts falling out. And we can see we got this nice binary stream at the top of the page there. But we need to validate it. How do we know this is real? So I found a spec sheet that references the data packet format. And it starts with a preamble, as many of these things do. And a preamble, for those who don't know, is essentially a constant unique binary sequence that tells the receiver when a packet is starting. But after that, it has a manufacturer ID following the preamble, and then a bunch more data parameters that we don't need to worry about right now. But if we end up converting that manufacturer ID to decimal, sure enough, it lines up with the actual ESN of the device that transmitted the packet. Like right on the back of the device, it says that ESN, and they give you a little card with it when we first buy it. So this means we're doing something right. We're actually decoding this data over the air. Now, the data packets contain just about any information. This is up to the end integrator. But these devices are really predominantly used for asset tracking and sending location data back. And everyone uses the same format. Globalstar kind of suggested this format. And if you use that format, it allows it to be digested on their back end. So after extensive comparisons, some of my interns, well, I don't think he's here, he helped me figure out that bits 8 to 32 are the latitude, and 32 to 56 are longitude. So you convert those bits to a binary decimal value, and then you multiply that by a degrees per count value, and that essentially extracts the actual latitude and longitude. And I'll be providing this code as well. It's listed down there, but you'll be able to try this out for yourselves. So data packets also contain a checksum. Long story short, it was kind of a long process, but figure out how to calculate the checksum. And highlighted over there is the actual checksum polynomial value. This means that we can not only validate packets, but if we know the checksum format, we can create our own. So note that there's no encryption on these packets, no signing, or any protections. It's really just data. So if we could transmit, to me that would seem like we could inject our own data back into the satellite network. So now recall that we're currently just receiving data on the uplink, but due to the bent pipe nature of Globalstar's satellite system, the data on the downlink is the exact same as the data on the way up. So reception on the downlink should be very, very, very similar. Except in this case, we need to compensate for Doppler shift. These satellites are moving wicked fast, as well as multipath interference. So this is an avenue for future research, but it shouldn't be that much harder to just start building our own base station. And really, with our own ground station, we should be able to see about a 2,000-mile radius around us. So now that we can create our own data, can we actually inject it back into the satellite network? So little disclaimer here, I know you guys are a bunch of hooligans and I don't want to be blamed for this, but seriously, don't transmit on Globalstar's frequencies. It's probably illegal where you live. If anyone actually knows the legality of transmitting from international waters, I wouldn't mind knowing. But you could interfere with critical communications. These things are used for emergency response. Fortunately, the Simplex frequencies aren't used for actual satellite control, so it's not like you're going to make the satellite fly sideways or anything. Yeah. But if you wanted to transmit, theoretically, this is actually the easiest part. You simply mix the data, PN, and carry together at the appropriate rates and send it out over the air. Now, I'm not going to release my transmission code for fear of something bad happening, but if you're reasonably technical, you should be able to use the information here to do it yourself. I'm happy to chat about it. But really, all you need is 0.2 watts of power. And you can easily get an appropriate amplifier on the internet. Excuse me. I ended up writing some GNU radio code to spoof data and do all this. But what if there was an easier way? So Globalstar provides an OSX firmware update utility for their spot trace devices. And inside this application package, there's a tool, spot3 firmware tool.jar. And it contains all sorts of interesting functionality that's never called by the consumer app. So we look at it, and there's this UI folder and a debug console.class. And it calls this function called write ESN, electronic serial number, in spot device.class. So what if we wrote a Java app to call that debug console, mystery debug console? Well, sure enough, it pops this nice debug console. Hidden functionality for everyone to play with. So this debug console lets us update an ESN. Essentially, we can change the serial number of any spot device out there, i.e. clone an arbitrary device and maybe possibly a target's device or what have you. So to prove this, I cloned one of my spot trackers with the other's ESN and told it to transmit out to the world. Sure enough, I got a tracking email email back that confirmed that I cloned that device. I then cloned my dad's and made him think he was somewhere else, and started to have a little bit of fun with this. But anyway, so those devices are currently on sale for $49. Go out, give it a try, low barrier to entry. So besides the obvious of utilizing the network to transmit your own custom data or expanding capabilities of your service, such as maybe transmitting data packets faster than your paid for rate, what can an attacker do with this transmission capability? Well, first, these devices are used in emergency response around the globe. What if an attacker spoofed thousands of false emergencies and jammed up the Central Emergency Response Center in Colorado, preventing aid from getting to an actual emergency? Or what if you monitored for help requests and then just canceled them? So I was talking to a really well-known reporter yesterday, and she used to work out as a correspondent in the Middle East, and her life was currently in danger, or constantly in danger. And she said that a lot of the journalists out there use these spot devices, the consumer grade, they're kind of low profile, to track their whereabouts in case they get kidnapped. So they're relying on these devices to protect their lives. Now think about this. What if a foreign adversary was sniffing this tracking data? These people had no idea this data was not encrypted, and I have a feeling they'll stop using them now. It turns out these chips are also used in access control systems for reporting, door opening, closing, et cetera, by law enforcement and for animal tracking. So I personally think it'd be hilarious to say that a wild grizzly, relocated itself to a suburban California neighborhood and just see what people do, especially one that they can't find. So no ideas here. I also forgot to mention that they're heavily used in SCADA systems across the board. And to refrain from naming specifics because you guys are, a bunch of hooligans. Maybe that's more the DEF CON crowd. But they're commonly used for water quality monitoring and pipeline pressure monitoring, and really actually predominantly in big oil and gas operations. So what if you're a rival oil company and you wanted to figure out where your competition was drilling? Well, why not just fire up your own base station and have a look for yourself? But wait, there's more. Lockheed Martin Flight Services, the FAA contractor that handles flight planning for the FAA, just allowed these devices to be used to track any VFR flight out there. So what if an attacker made an airplane appear to deviate from its intended flight plan into tightly controlled airspace? Could you screw with an airport? Maybe. So to demonstrate some of this, I built more of a full feature capability to really just see what I could do on the cheap. So the way it works is that I sit with the device in the uplink path of the transmitter and listen, on the top of a high building. I had this running in my casino room last night, aim it towards the airport. But over time, I'm able to pick up countless transmissions from asset trackers and map their pattern to life. This makes it really easy to identify what a target is by where it goes. In this case, the scenario I'm going for is monitoring an armored car route. I did some research a while back on location-based privacy with mobile apps, and I tracked a bunch of users through their mobile app locations through a broken API. I was actually able to correlate real patterns of life. Where is their home location, where is their work location, or figure out who they were from that. So this stuff really does work. It's very important to know, where something's going and where it intends to be. Anyway, now this is where it gets fun. You kind of think opening scene from Fast and the Furious where they hijack the trucks. So now that I know where the armored car is, I know when to hijack it. So I hijack the car, disable their beacon, fire up my beacon, and begin spoofing their beacon's ID from my transmitter. And I also spoof the GPS coordinates to make it appear that the armored car is on its route. But in reality, I'm driving off somewhere else with all Fort Knox's gold and getting away with it. So you might ask, does this work? Short answer is yes, but we need a high vantage point. So clearly the only real solution was to go out and get my pilot's license so we could intercept data from the air. Some said it was a little excessive, but no. But anyway, so let's see how this works up close. I decided not to tempt the live demo gods today, so I've broken up the process, really just what you see on my computer, into a step-by-step video to show the despreading process, like one of these data packets you intercept from the air on top of a building, piece by piece. So I'm going to exit here and switch over to a video really quick and pray to the video demo gods that, let's see, demo. Does that go? Can you guys see that all right? All right, is that playing? So we're going to fire up a new radio here and wait for someone to transmit some data. And there you can see a data packet being transmitted, and we automatically record it to file. So then we'll split over here to the despreading code, and essentially we'll drop that file into the despreader and give it a go. And you're going to see it lock on to the PN sequence immediately and start correlating. Now it takes about a minute, so I'm going to kind of fade through half of it so you don't have to watch. And then you can see a fairly consistent correlation from the data packet across the board. That's what you want to see. You don't want to just see a bunch of random data. So we're going to go ahead and play that data so you can see. And you can see that sharp spike emerging. And then we're actually writing out the bits from that sharp spike to file. And I'm going to zoom out on the time domain representation there on the scope. And you're going to see actual data bits flying over the air. So those are satellite transmission data bits. So from there, all these data bits are being written out for a file for us to interpret. So we're going to go ahead and interpret those data bits over here. And it's going to output the binary sequence for what they actually are. And go ahead and put those into our packet validator. And sure enough, there you go. There's packet data right there. So you could drill in further if you wanted to and pull the location data out of that data field. But this is essentially the process of intercepting this data. So let's go back. All right, so a few parting thoughts and conclusions here. I disclosed to Globalstar about 180 days ago, and they were actually really friendly in their response. It took a while to get back to me, but they seemed pretty concerned. I feel like they just don't deal with this kind of stuff a lot. I ended up providing them a lot more technical details, and I never heard back. Wired broke the news recently initially, and I think Globalstar had to issue a response, but they issued a statement saying that they take privacy really seriously and have monitoring in place to detect these attacks. Unfortunately, half this attack is passive, and so you can't detect that. And the transmitting portion, if it's targeted, I think it has a really low probability of being detected if everything's really within the parameters of the system. So I sincerely hope they're serious about addressing these issues, and I really look forward to seeing their solution and how they address this. But there's still a lot of work to be done on this code, and I'm releasing on GitHub, later today or tomorrow as soon as I can get it up. Follow me on Twitter. I'll post on there when it's up. But I'd love to collaborate on this and improve the whole system and maybe begin intercepting these downlink signals. And I have a feeling we're only seeing the tip of the iceberg on where the system's used. It'd be interesting to aggregate a ton of this data and start taking a look for ourselves. So if you're interested, please help out. But in conclusion, I really still think Globalstar makes a great product. I still use them myself. But manufacturers, remember that aerospace products have a long life cycle, and we're stuck with them for years to come. The way the Globalstar system is implemented, it's really unpatchable. Most of the devices don't support firmware upgrades, or they're so far out in the wild that you're never going to get to them to patch them. So the best thing to do going forward is to add a layer of encryption on top of the existing protocol. And remember that obscurity is not security. Spreading your data won't protect it. So consumers, assume someone can snoop on your data and act accordingly. And hold manufacturers to a higher standard. Demand security and really demand to know how your data is being sent and is it encrypted, and if it is, how so? So I want to give a special thanks really quick to my interns up here in the front row. They helped with a lot of the testing and kind of some of the grunt work. And a big shout out to Synac for funding the crazy research. But the code will be live later, and I'll be sure to tweet when it's up. So anybody have any questions or comments, thoughts, concerns?
We showed it to the company already.
So the question was, have I showed it to the company already? And the answer is no. I disclosed to them, the research and findings, but I haven't actually demoed to them or had a face-to-face conversation about them. And if there's a Globalstar rep here, I'd love to chat, maybe to see how we can get this fixed. Anybody else? Let's see. Is someone over there? Go ahead and just shout it out. Yeah, right there in the back.
Is there something like that used for home arrest?
I'm sorry, I couldn't hear you.
The devices that are used for home arrest with same?
I'm actually not sure. I was looking around trying to figure that out. I think they might be, which would be really interesting. I'm sorry, the question was, are the devices used for like house arrest? So for like the tracking anklets. And I'm actually not sure. Be interesting to find out. Yes, right here in the front.
So it is a layer of encryption, a very simple layer of encryption. And would that stop where you
I mean, I guess the answer is I'm not really sure. The devices would need to be individually keyed from the factory, I think, because there is no way to do a two-way data transfer. Potentially, but I think it's better than the initial setup. So, maybe go to chat with them about it. Anybody else? Yes, sir, right here.
Was it Iridium?
I'm sorry?
Iridium data.
So the question was, have I looked at the Iridium data network? And I actually haven't. My guess is that a lot of these systems are kind of built very similarly and probably vulnerable. But part of this is I kind of wanted to show you guys how to do this. So maybe you guys can take a look at it yourselves. But I'd love to, and if I do, I'll certainly let you know. Yes?
Why do you think that people have not encrypted them? Do you think it's a processor limitation of?
Yeah, good question. The question was, why has the data not been encrypted? The system was designed in the 90s and deployed early 2000s. I think security probably just wasn't at the top of everyone's mind. Not to mention, I think key distribution in this unique keying setup was probably a little bit harder back then. But there's really no excuse now. I think, satellite bandwidth was probably a little more expensive and precious back then, and any additional overhead probably not worth it. But now going forward, I think we can do this, and it shouldn't be too hard to layer something else on top. Anyone else?
Right here.
Yes, sir. Right there in the back.
Did you ever hear data coming across as far as what satellites it was communicating with?
You say any data for which satellite it's communicating with? So it's actually, there's no satellite specific, the question was, did I get any satellite specific data? There is no satellite specific data in the packets. It's actually all the different satellites just repeat whatever data they see and really don't interface with the device at all. All right, guys. Well, thanks a lot for coming out. Feel free to come up and chat.